Differential equations. We're in section 2.3. We're on our second day, and from the first day, please remember that we talked about solving this linear differential equation by use of an integrating factor. The integrating factor we would find by taking e to the integral of p of x dx. And we're really going to review that today. And the only added component that we're going to do, and our textbook does this quite frequently, is we'll have an extra day of practice, but now we're going to deal with this initial value. 0, 4, y of 0 equals 4. When x equals 0, we have y equal 4. So as we're looking right here, you can see that our p of x is a 1. So our integrating factor, as we're working this out, we can say e to the 1 dx. Well, it's only going to take us the briefest of moments to find that this is going to be e to the x. This is going to be our integrating factor. So what did we do the other day? Well, we multiplied every part of this differential equation by the integrating factor. And the purpose of this is that now we can look at this left-hand side and say, really, this is the product rule. In fact, it's the derivative of e to the x times some function called y. And we're always going to make use of that. We want to write it that way so that we can then integrate the left and the right-hand sides. Obviously, the left-hand side now will just become e to the x y. Take a look at the right-hand side. If that looks oddly familiar to you, you can do integration by parts in the shortcut method, the tabular method. Take your component, your algebraic part x, continue to take derivatives of it. The derivative of x is 1, the derivative of 1 is 0. Continue to take antiderivatives here, and you'll just get e to the x. We'll have a plus, we'll have a minus, and what are we going to see? Well, this is x e to the x minus e to the x, and don't forget a constant. Well, this is where we would have stopped last section, but now we can say, look, your initial condition is x equals 0, y equals 4. So plug in x equals 0, let y equal 4, and we are going to solve for c. So this left-hand side becomes just a 4 because that's a 1. This is 0. E to the 0 is 1, so this is a negative 1. And it will only take you a moment to see that c equals 5. So, taking a look at this right here, we'll have e to the xy equals x e to the x minus e to the x plus a 5. Now, please understand, solving a differential equation really means get y alone. Solve for y. So that's what I'm going to do right here. I'm going to divide by e to the x. Here, this will cancel out. This is just going to be a 1. You can leave this as 5 over e to the x, or you can bring that up as e to the negative x. And there you have it, a particular solution. And our function is never going to be undefined. So we can even go further and say this would be occurring on the interval from negative infinity to positive infinity. This idea of intervals is actually very important, especially as we go to our second problem here. Our second problem, and you can see pretty much it's going to look so incredibly close to the same problem that we just had because of our integrating factor. Look at our p of x, it's just a 1 here. But what's going to be incredibly different you know that y is continuous. That's going to play a role later on. And it's continuous on the interval from 0 all the way up to infinity. Look at the right-hand side. F of x is cryptically written that way. Y of 0 equals 0. We've got an initial condition of 0, 0. But here's where we can have a sense of panic, perhaps. Kids will think, oh my gosh, look at this. F of x is piecewise. Yes. All of a sudden, this idea of having an interval is incredibly important. So, look, let's just say that, look, f of x could be two different things. We have to really pay attention to this assignment. If x is between 0 and 1, your f of x is equal to a 1. So we'd get dy dx plus a 1y equals, well, f of x is just a 1. Now, your integrating factor is going to be identical to what you just did in the very first example of the lesson. If you think about it, that's what we had right here. We had that 1y. We found our integrating factor real quickly. So what do? Well, we multiply every part of the problem by e to the x. And then we can say, well, you know what? This is really a product rule if you think about it. This is e to the x times y, the derivative of that. And then we can take our antiderivative, we can integrate here. This just becomes e to the xy. Here's your right-hand side of e to the x plus some constant. But guys, you want to make use of your 0, 0. And it's going to really say it's e to the 0 times 0. Here's e to the 0 plus c. So we get a 0 is equal to 1 plus c. C is equal to negative 1. And guys, at this point, I do want to just call to your attention that we had e to the xy is equal to e to the x minus a 1. So, hey, that hopefully is not looking so bad. We can divide by e to the x everywhere. And we'll have y equals 1 minus e to the negative x. So that looks good. But please, please, please remember, this is on a particular interval. This is only when x is between 0 and 1. Well, there's more to the story, isn't there? We assumed that we were working this problem out only between x values between 0 and 1. You could very quickly say, now wait a minute, it's very possible that x is greater than 1. If so, your f of x is going to change. So this is why it's so important to pay attention to this piecewise function right here. And we will have dy dx plus our 1y, but now your right-hand side is just a 0. Well, guess what? Your integrating factor is the same. You know, we already worked that out. And we're going to multiply everything by e to the x. E to the x times 0 is a 0. Likewise, this is the derivative of e to the x and y. And we can integrate. And sure enough, you'll get e to the x y. But over here, we'll have some other constant. We'll have, say, a c2. And, wow, we can solve for y. C2 over e to the x, and we can even say that's c sub 2 e to the negative x. And this can seem to really trouble us some. We can think, gosh, is there a way to find that second constant? At first, you can think, no, I don't think there is. But there's a hint. See, here's something very, very, very subtle. they're telling us that y is continuous. You can think, well, how does that link in? Well, yeah, we've got two different intervals, but they're joined at 1. If you're going to be continuous, the y value that you're getting at x equals 1 here for our first solution has to be the same as what we'd get for x greater than 1 solution. To be continuous, that's going to have to be true. So what are we going to do? So we're going to say to be continuous at x equals 1, if I plug in a 1 here, we will be able to say that e to the negative 1 minus e to the negative x should equal this thing right here at x equals 1. That's the separation point. So look, we're going to have e to the negative 1 right here. This is c2 e to the negative 1. And tell you what, I'm just going to solve. I'm going to divide everything by e to the negative 1. This is the reciprocal. It just becomes an e. This cancels out to just a 1 itself. Guys, look at that. You found your second constant. So what are we really saying? Y is going to be this e minus 1 e to the negative x on this interval. So if we wanted to write this as a general solution, we'd say, well, the first answer that we got when we worked this out, that was true for x between 0 and 1. We just came up with this other solution right here, and that's going to be true if x is greater than 1. Of course, to be continuous, when you plug in a 1 in either of those assignments, they must be equal. And that wraps up 2.3, Day 2.